Hello, welcome, welcome. So, um, I kind of have an itch to build another CPU. So, these are the features I'm kind of thinking about. And I think this series is going to be more of, I don't know how to call it, kind of a build montage, I guess. Um, So we'll see if I can get some music to play while I'm building or something like that. But if you want more commentary on what I'm building, I would refer you to my other series. So this one will be more. I'll comment on some of the interesting parts, but I don't want to get too bogged down in feeling like I have to say something clever all the time. So this will be more of a let's get back into making videos for YouTube kind of series. Hopefully that's okay. So I'm not going to go over the features too much. You can pause the video here and read them if you'd like. Let's just get into it. Yeah, let's just start. So the best place to start is probably just to get adding working like usual, kind of the same way I got my last CPU working. So let's do that. Okay, so we've got some adding going on here. We've got, yeah, um, a couple of inputs. Yeah, I think this is a little bit too simple to kind of demonstrate much, but it's a start. So let's get something a little bit more complex going here. So I'm curious how this is going to work with this RAM because I need somewhere to store the stack machine. So yeah, let's tinker around with this. Um, let's see, how does this work? If we put something in here, let's do our classic 42 here. I guess this is the address. This is the value I'm going to put in there. I'm not sure what went on there. So, yeah, one of the issues that I have is that it's very difficult to find a time during the day when I can actually record. I have a son now, and yeah, he just loves to make noise and is not predictable at all. So, yeah, that is what it is, I guess. Okay, so I was just interrupted as usual. these are a little bit confusingly named, but I just want to figure out how does this RAM work? Like, when does it store things, and when can I read from it? Because this might not work. I might have to try some of the other RAMs that are available. So let's see. This, I believe, is the no, that's the in. This is the address. This is DN. So yeah, this is the one that I want to change. So, and then if I do this, nothing happens because it doesn't store. If I do this, I think I keep double clicking by accident. So I just clicked it once and nothing happened. Interesting. So if I stop storing and I click it again, yeah, so there's a 2-cycle delay. So that's not going to work. Yeah, I honestly don't know what kind of RAM this is that it has a 2-cycle delay on write. I guess it's a block RAM. Yeah, this is a block RAM. Interesting. I did not realize that there was a block RAM that behaved that way. In the FPGA, we'll have to use distributed RAM. So I need something that behaves more like distributed RAM, which would probably be a register file, but let's see. We always have this asynchronous RAM, but I'd like to avoid that. That's a bidirectional. This says it's block RAM, but let's see. Of course, gotta change the bits. Okay, so if we put in 42, we're storing, and we clock it, nothing happens. So why is this different than... What's the difference between these two? That's block RAM, that is not. So maybe I used block RAM by mistake before? Yes, I must have. Yeah, because the store is in a different position. Okay. What am I doing? Okay, and then we always want to load. Let's see if this one behaves differently. So we store, and then we clock it, and it instantly shows the result. I think that's what we want. And then what happens if we change the address? Oh, well, we'd have to stop storing first. Yeah, it instantly updates when the address changes, which is, I think, exactly what we want. Because we need a RAM that behaves exactly like an array of registers would. So an array of registers, if you change the address, then it would instantly update because you're just selecting a different address on a mux on the output. But then storing would only happen on the clock edge, which is exactly how this is behaving. So I think this is what we need because this will basically behave the same way as distributed RAM, which is just an array of registers, essentially. Distributed RAM is designed for like register files and that sort of thing. So let's run with this as the stack storage and see how far we can get with that. I'm kind of thinking I need to get the stack working, like pushing and popping from the stack before I get into putting an adder on the stack. So I think I'll just delete that and try and simplify as much as possible. I want to get pushing onto the stack and popping off of the stack working first. Okay, I don't know what this is going to do, but say we want to push 42 onto the stack. Push. So then we've got 2A here, and then if we push again, it does nothing. Okay. Direction is wrong, but let's make sure that we can see what the stack pointer is doing. Okay, so it's decrementing, which I think is what we want. Can we see what's in here? Should be at the bottom. Yeah, so it is pushing. Okay. All right. We just have no way of basically reading it. So if we undo this, then it doesn't show what's actually in it at this point. Yeah, I don't think a counter is going to work. I think we need to have a separate adder and a register, because a counter only updates when the clock pulse happens, which is not kind of what we want, because we need to, I think it's post increment, pre decrement or something like that. So we need to do the different operations at the different sides of the clock, essentially. So, let's see if we can figure out how to use an adder and a register instead of a counter. Okay, this kind of seems to be working, at least for pushing. The stack memory at the bottom has 2 entries. The 0 entry was not changed, which I think is what we want. I am post decrementing, though, which I find a little bit odd that it didn't store the first value in 0, because that's what the register would begin at. So let's see. Yeah, it's 0. We've got store. Because the value in toss here, the top of stack, that's what that stands for, by the way. The value in the top of the stack is 0. So if we don't store, but we don't have a way to disable the decrementing. Let's add that. I think it's just as easy as doing this. Okay, so if we're not storing, what we put in here, or if we're not pushing rather, should update toss. It does, but we haven't put it into memory because we're not storing. So as soon as we push, it should put that at address 0. Now, I'm not sure that that's what we want. I think we need to post decrement, because this is this is post decrementing. We want to pre-decrement. We want to put this after the register here, I think. Okay, let's try that. Okay, let's see if this does what we want. So we put 42 in there. We clock it so it's in the top of stack, but it shouldn't have been put here. If we push, the stack address becomes -1 essentially, which is what we want. I think that's what we want. We might actually want it to start at the top of stack. I mean, stacks usually grow from the bottom, which is why I'm doing it this way, but that might pose problems later. I mean, we can always change it later. So, okay, so I put it in there. It did not go in 0. It went at the bottom, which is what we want. I mean, it would be nice if we didn't have to scroll all the way to the bottom to see what's in the stack. Yeah, I think growing from the bottom is going to be a mistake because it's going to be more confusing. Well, if we grow from the top, then we post increment because we want to store the first element at 0. So yeah, let's just do that and see how that goes. Okay, let's see if this works. Change top of stack first. Okay, it's in the top of stack. We push, which we don't want this multiplexer here, I think. Yeah, because it changed the address to 1, so the first element will be at address 1 instead of 0, which is not what we want. Yeah, let's fix that. Okay, I think this is what we want. So we clock it into top of stack, then we push, and that ended up at the top of the stack, which is what we want, or the beginning of the stack, I guess. Okay, so if we do a different value and clock it, then we should have the 2A, and then if we push again, then we'll see the 15. Okay, all right. So we need to be able to pop the stack as well. So let's see how that would work. Okay, let's see if this works. So we set up the top of stack with a value. I'm guessing we're not going to be able to do that because this link is not correct, because we'll want to pop into the top of stack. But let's see if we can get this part working, at least. So let's push a new value here. Let's just increment it. Makes it easier. Okay, so we should have those values in the stack memory. So we stop pushing and we pop instead. So when we do that, we've got this value that we're outputting, which I think is what we want. And then it didn't save. Okay, so there needs to be an OR gate on the enable for the stack pointer. Okay, that should be easy enough. And then of course we need to be able to pop into the top of stack. So do I want to have separate controls for that or not? Yeah, let's try and fix those things. Okay, let's see if this works. So we, as usual, preload the top of stack, and then let's push a few values here. Okay, stack memory has those 3 values. Then we let go of push and we pop instead. So we've got 2D up here, and we have 2C in here. 2C is up here now, and we've got 2B down here. 2A, 2B, and we're at the bottom of the stack here. Be nice to have like a stack overflow somehow. Not sure how to implement that. Or I guess this would be technically an underflow. Guess we can look at the sign bit on, no. Like comparing the sign bit, I guess. But anyway, we add that later. Okay, I think that worked. We were able to push them on and then pop them back off. At this point, I'm not really liking having 2 different signals. It kind of seems like in order to read, we need to be pre-decrementing anyway. So I think I'll put those on the push line here so that if neither of them are active, then it'll be reading what's in the stack, which would be at -1. So let's do that. I think this should work. So it's reading past the bottom of the stack at this moment, but that's because there's nothing pushed on it. So this could be like an underflow warning, potentially. And then if we put stuff on there, we can just put something in the top of stack for now. Okay, and then we put on, we're going to push now. So we would push to A, to B, to C. Those are in the stack memory, which is what we want. And then if we undo this, then that is looking at the second on stack. That's basically exactly what we want. In the future, we'll want 2 registers that are kind of buffering the top of the stack because we need access to 3 values in a few instructions, like the select instruction, for example, which would select one of the bottom 2 registers based on what's on the top of stack. So then that operation would need access to 3 different values. But I think this is good. And then if we pop, then it should put 2C back into toss, the top of stack, which is, I think, what we want. Yeah. And then we can pop again. So, and if we stop that, yeah, if we stop that, nothing happens here because we're selecting the next operation on the stack as we want. Now, what happens if we put both of these high? I don't even know what just happened. I think we'll just call that undefined behavior. It does something random if that happens. None of the instructions do this, I don't think, or we can make sure that none of them do anyway. So I don't think we have to worry about this particular case, but we do need at least 3 states. We need push, read, and pop. So we kind of do need at least 2 bits to handle the control of this unit. Yeah, so I think this is working perfectly. It would be nice to have the extra register because we will need it. Might as well get a full, stack working in this video. So let's do that. It's also kind of busy, so maybe we can clean this up a little bit as well. Yeah, work on that. Okay, let's see if this works. So we want to push. Let's see what will happen. That'll just put it in the top of stack, which will also put it in the next on stack. So top of stack, next on stack, and then Ross would be third on stack because the R is, yeah, I don't know why. We could also name these like XYZ or, something like that as well. I'm just going to go with this for now. So if we do this again, it pushes. So I think we actually have to do this enable via this, or maybe actually this here, probably. Yeah, let's try that. Okay, so if we've got 42 here, we clock it, it should only go into the top of stack. So if we change this to, yeah, okay. And then if we push, and I'll just change this, then it goes into the next on stack, which is what we want. And if we push again, what just happened? It should have gone into, oh, it is there. It's just, we can't see it. Be kind of nice if the stack was dual ported and we could read the other address. We could maybe do that by buffering. Yeah, we could have 3 of these registers and then the stack value wouldn't be visible. I don't know if we want to do that. Yeah, I'll figure that out later. So if we pop, then it should route to B to NOS and to C to TOS. And it does. And then if we stop popping, yeah, I think this is working correctly. I am not 100% sure that I want the enable here to be controlled by pushing. I think I probably want separate enable for the top of stack. Yeah, I think. Yeah, I'll do that. Yeah, I think if we toss, which is right enable toss, is low, I think we don't want this mux to switch. No, does it matter? I don't think it matters, actually. Because if this is low, then this won't save, so it doesn't matter what the inputs to it are. Yeah. I think we don't really have to worry too much about that right now. And in fact, we could probably just tie WeToss to push. Actually, we do, because operations will pop from NOS, so it'll load from the stack, but we'll be writing to TOS in the same cycle. So we do want, yeah, let me play around with some things and see. I think we kind of just need more of the CPU built first before we can kind of decide how this is going to work exactly. So yeah, I think I'm going to do that in the next episode. So in this episode, we got basically the stack working. So we've got a way to pre-increment, I think it's doing. Pre-increment on push and post-decrement on read or pop. We've got stack memory that allows us to read what's ever in it in the same cycle, but it's clocked on writes only, which acts like FPGA distributed RAM. And this stack here, I've got a 12-bit address for now, but it's probably going to be not very large in the long term because distributed RAM is expensive. I might go into that. I don't know. But anyway, this is probably going to be pretty small, maybe 16 registers, something like that. And then there'll be another circuit that kind of offloads that to memory at some point, just to make sure that context switches are fast. But we're so not there yet. So I left this as being decently large. So then we can just not worry about that until we get to the point of needing fast context switching. And then, yeah, we've got a couple of, I guess you could call them cache registers that allow us to, which allow us a little bit more control over the top two items on the stack. But we do have some access to the third item. Yeah, I think this is a good place to call it. Thank you very much for watching. There will be links in the description to a GitHub repo for this. And actually, I'm going to put a link to the GitHub for this project in the description. So then you don't have to copy it from the video, but if you want to copy it from the video, that's where it is. The program I am using is Digital. It is by H. Neiman. So if you search for his name and the word digital, you'll find it on Google. There will be a link in the description of this video for this program as well. I think that's all of the housekeeping. If you find this video helpful, you know what to do. There are links in the description if you feel generous. Anything is appreciated. I don't make very much off of ads on these videos, like pennies. So anything else is quite appreciated. And yeah, I thank you very much for watching. I hope you have a great day. Bye.